All right, thank you, Rasmus. Now I hope both my sound and the picture is viewable and you can hear me.
Perfect.
So I want to talk about, and if you have questions, just post them as Rasmus said on the chat, and we can also do them during the talk, so it can be on the slides where you have a question, so we don't need to go back, because it is information rich looking at bit different aspects. So let's see how we go along. To set the stage here, I went to a conference, the NR conference in Brazil. That's 6 years ago. And in there was a nice presentation by a person that had measured 24 samples using NIR. And it did single measurements on each of these 24 samples. And then he had measured a lot of references on these samples, and among them was the amino acid profile of each of these samples. And he made 32 PLS models, and he was very happy because they were all, working reasonably fine, giving nice correlation coefficients and low RMSV values. So everything was fine. I did raise my hand and I asked, so you have 24 samples and you have 32 references. Are these all independent? And then he closed down and didn't quite understand what I asked about. And I was thinking, I realized maybe there's some issues here that would be sort of nice to address, and not that it hasn't been addressed before, but I think I would like to readdress them. So a bit of another example here is from Bali. Now, those of you that have been working in Copenhagen can probably guess where this Bali data comes from. And yes, it is from Lars Munch. And so these are 4 parameters. We have the amide content, the beta-glucan, moisture, and protein, and we can make PLS models of each of them and get reasonable RMSV values and nice R squared. Everything is fine, of course. Everything looks good. Then the question is just what we do have as an issue, or could be an issue, or is it an issue? I think that's more like the general question. There's some correlation between these different reference data. And we can see here what we have here, then the 4 same parameters on the y-axis and also on the x-axis. And of course, on the diagonal here, it is, these have been flipped around, sorry about that. So now you have to be a bit creative and you have to put the protein here in the first column and then flip the others. What you can see here is that the moisture content and the beta-glucan, well, that's actually quite high correlated with an R squared of about 0.85. That does mean that if you're making a PLS model on beta-glucan, you're probably going to use a lot of the moisture content as a predictor, because they are so correlated. So it's difficult for the PLS model, or the PLS model does not see the difference because it doesn't care if it's an indirect or a direct correlation between the parameter of interest and what it is that you're predicting and what it is using, of information. Now, I think the first time I really started reading a lot of papers on this came first on, so here I have some examples of what I'm going to go through first. Sorry for that bit of confusion. So start off, actually I'm flipping around a bit of order here. So I'm starting off with these fatty acids, and that is done by a physician called Daniel Berhe, but with a lot of help from Carl-Emil Eskilsen. And then I want to continue on with my own article on the prediction of glucose and fructose in wheat straw, which is a bit based on the work here by Daniel and Carl-Emil, but also some of my own ideas on top. And then again on a paper here from Jing and me, among others. Again, a bit looking at the uniqueness properties, the same idea about the cage of covariance. Now, you can also in the same ball game start to talk about, okay, how to get, handle interference in data. So I also have then 4 different ways of handling orthogonality issues. Some of them you probably have heard about before, and there may also be some here that you haven't really heard about. So first I have one called direct orthogonalization. That's by Klaus Andersson, and that's back from '99. I don't think that has very many citations, to be honest. It was actually based on some work by Svante Woll here in '98, which is called the orthogonal signal correction, which I'm also going to talk about. And then, which you may know, but probably the one that everybody does know, is the OP-less that was suggested by Johan Trygg and Svante Woll in 2002. And then Academy nicely pointed me towards a paper here that Peter and him, Peter Sko and him published just this year, which is also a nice way. And I think there's actually a nice link between the first one and the last one here. We take it back to. We got that far. So the first 3, they are more on example sites. So we're going to sort of look into, okay, what is the problem, what is the challenge here, and how it can be viewed in related to the K-Joe covariance. How can we see how things are related and how things are not related? So let's go into the total fatty acids. So I said I changed the order a bit, and that's because I rearranged my slides a bit early today, and then I forgot to rearrange my summary slides. Sorry about that, but I hope that you can follow anyway. So what we can see here is that we have then measured the total fatty acids, and we measured the individual components of the fat in Borg back fat. Sorry. There's a nice correlation for all these models of from 0 to 0.78 to 0.90 in R-squared value. That looks all fine. However, you can also see that many of these prediction models, well, they are indirect. And why do we know that? Well, if you know something, this is based on Raman spectra. If you know a bit about Raman spectra, probably it's difficult to sort of separate several of these individual fatty acids from each other, spectrally speaking. Now, the summary of all the results that they did can be seen in this figure. I'm sorry. I don't know why there's a big tag, at least on my screen, on where that figure has been stored. But what we have here is that on the x-axis, that is the model performance. So that is when we have made a cross-validation model, and we can see how well does it perform. So that's the R-squared of the cross-validation. On the y-axis, we have how well is it actually related to start with, like what's the general correlation together with the measured iodine value. And you can see that, well, up here on the right-hand corner, we have the good models. They have high correlation beforehand. And also when we start doing the cross-validation, they do have a high correlation. And for many of them up here, it seems that there's not that much difference between the circle, which is the correlation that we have together to the iodine value, and then the star, which sort of indicates how well it is, and we make the prediction model. But we do have, especially here, you can see some of the individual fatty acids where there's a huge difference between the two. What does that indicate? Well, it certainly indicates that the model that we have here is very much dependent on that the correlation to iodine value stays the same. So we can also try to dig into what that means. We're going to see some examples of that a bit later on. But what they also nicely showed was that, well, you can put this up a bit more mathematically, let's say. So you can create a V matrix. Well, that consists of a set of ones. So this is a vector of ones. And then you have the reference of interest, or the analyte of interest in the matrix. You can even have several here. And what you can do then, you can project that onto your X to get an XK. Now this one here is then dependent on this K analyte. That means that now we can split up our data to being something that is not dependent on the K and is dependent on the K. So that's two different parts of your data. That also means that we can now have, and we have our predicted of the component of interest? Well, we can say that that's one part of it is related to what we're interested in, and another part, of course, is then related to some unique part or some other interference. And I had then made a nice figure. You can see on the right-hand side here, you can see that, okay, how much of this prediction here of the eigenvalue is dependent on the eigen? Well, it's high, of course. And then how much is independent? I'm not quite sure how we actually did this, the one column all the way to the left, but all the other ones I can relate to, meaning that you do have some part that is unique for this model and other part that is it's just dependent on the eigenvalue that it has. So there are two aspects there. And so this idea here kind of indicates that for some of these parameters, you actually get a reasonable model. It is actually telling you something of your parameter of interest, and not just that it is correlated, happen to be correlated with the biggest reference here, which is the eigenvalue. Because everything from the right and down here, so everything from eigenvalue to the right here, well, they are just subfractions of the fat. So you can see that all of them, and that's also why it makes sense to see, okay, how much are they dependent on this eigenvalue, which is the overall parameter. Now, that brings me to another example, and this is for straw. I was contacted some years back by some people working with the conversion of straw to ethanol. Yeah, this ethanol is not for drinking. It's actually for used in the biofuel industry. So that's a side thing, I would say. Anyway, so we have this nice big ball of hay. Now, and we measured NIR on that. That's what we see on top here. And to the right-hand side, this is really what's going to happen. So you take the straw, you add some enzymes, and these enzymes will break this cellulose and hemicellulose from the straw into glucose and cellulose. And then we can add yeast and we get ethanol. Now, what would really be nice to know is that, okay, can we measure the NIR here and get an idea of how much glucose and cellulose we get after the enzyme degradation? Why? Well, because then we can know, of course, before you start the process, how much you actually can expect as an output at the end of the day. So just want to show you the data. So what we have here is that each of these colors, that's a location. And then these are both from Denmark, and there are also some from the UK. Doesn't matter where they're from, but just to know that they're all from different locations. And what I've done here is that I've taken out the dark blue ones. You can see that they're sort of in the middle. I said that, okay, well, they look to be in the middle of all the samples, so I take them out as a test set. It's not completely independent, I know, but at least I haven't been looking at Y yet. So I'm just looking at the X data, so just looking at NIR of these data. Then I can make then a glucose model. So that's what we see here on top. We have an RMSE that is 0.017. Now, of course, this is highly dependent on the range of the glucose values, and it should say that this is fairly low, it's not a perfect, and you're going to see a bit more on how it looks like. But this is reasonable. This R squared is about 0.8 or something. And you can see that no bias, which is, of course, sort of has to be, since we're only looking at the cross-validated data. And the slope is close to 1, which is also to be expected. Now, xylose, fairly much the same RMSE and the same bias and slope. And just the range of both of these two parameters, so the xylose and glucose, is about the same. So everything is good and fine here. So they both look reasonable. Now, let's look at the correlation between these two. And if you look, now I've just plotted the reference analysis of the xylose and glucose. And we can see that so we have glucose here on the X, and we have xylose up on the Y-axis. And we can see that the correlation between these two is rather high. It's 0.82. Now, when I started looking here, I was thinking, okay, but is this the prediction of the silos and the glucose? Are they independent or are they somehow related to each other? And at the time, this time, a paper from that I just referred to on the fatty acids that had just been published, and I looked into that and started thinking how to do it on this data, and then I came on to a, let's say, a bit more pragmatic idea of how to look at the data. So I created two new subsets of the data where I only looking at some very small parts, some very few selected samples. So I selected out one sample set here in yellow with regards to making a model on glucose. You can see that I have quite a wide range of glucose samples going from 0.16 and up to about 0. I'll have one here all the way on to 0.32. So very wide range here, while the range on the silos is very low, meaning that I have reduced the correlation. And you can also see that, you can also appreciate it here. Now it's this correlation between the two is 0.44. Now in the purple, I've then selected some samples that I want to build my silos model on. And you can also again see here that we're going then from about 0.16 up to 0.26 in silos values. And again, the amount of the difference in the glucose values is very small, leading to here an R of 0.32. So again, reduce the correlation between the two parameters drastically from the 0.82 that I had in the beginning. Just use, oh, no, can use. Let's see if I want to can use my pointer now a bit more actively. There you go. So you can see here that this value up here, the 0.82, well, that has been reduced in both of these two data sets. So now I created two new data sets that I will then use, that I will base my model on. So that's what we can see here. We can see that we have here now I called it RGS. That's the model for glucose. And then I have one from silos just below here. You can see that they're very similar to the one made on the total amount of data. So here we have an RMSE of 0.015, slightly better. Slope is slightly worse, but not much. And for silos, same RMSE value, and the slope is basically the same. Maybe slightly, again, slightly worse. But what is more interesting now is to look at the test set. So remember, if I go a few slides back, you can see that here I've taken out these blue samples, taken them out as a test set. Then if we start looking into how they are predicted, we can see in the first line, now that's if I look at all data, then the Abbott looks reasonable. The slope is it's not really close to 1 anymore. So obviously there's some issues here with the glucose predictions. And if you look at now, when I have broken the correlation to silos, you see that the prediction here gets a lot worse. And also there's starting to be a bit of a bias here, quite a lot actually. And you also have some slope issues. So there are several issues here with the glucose model. If you look at the silos, on the other hand, you can see that, yeah, the prediction towards the Abbott test set becomes a bit worse. And that's probably because this lowest one has not been, haven't been able to span the whole silos range in this model. So we are predicting, we're actually extrapolating for some of these samples. The bias though is fairly low, and we are keeping a nice slope here. How does that look like? So if you're then looking at the silos, so we can see that we have, this is the stars here, the black stars. Well, that is the cross-validation results of the silos model. And then in red, we can see how the Abbott or how the test set is behaving. And they look reasonable, they look similar. So it seems doable. It seems like actually the silos predictions, but it's actually based on silos and not on anything else. It's more directly related to what we have, amount of silos in the samples. If we look in the glucose model instead, we can see that the blue ones, that's where we have the cross-validation results. They look reasonable, and you can see here again that, yeah, I'm saying reasonable because we do have a spread here. There is some variability, but at least we can get an idea of low versus high amount of glucose. However, if you start looking at the red dots, which again is test sets from Abbott that I've taken out, the correlation here doesn't seem to be super good. And if you had taken away all these low range samples, there would be really no correlation. So obviously there is an issue here with the glucose predictions that has a very low correlation. Now I started talking with Jan at this point and Sander, that were my two collaborators. There were also others, but those who I had most contact with. Okay, how could this be? And actually, if you go back into how his whole production is, it also made sense because I want to just show you one slide first so that I get in. So we have here I'm going to get back to why this makes sense. But first of all, just looking at, we can also look at the same way as what Daniel and Carl-Emil did before. We could sort of look at, okay, how much is the commonality and uniqueness part of these different models. And again, I think I would focus here on the glucose model, so the RTS and RGS models. And we can see here that when we have based the model on all the data, we can see that there's not so much unique to the glucose. Most of it is common also to the xylose. Or when I have broken the correlation, we can see here is that the process of reducing the correlation between the two also means that now the new model here is actually focusing on the glucose variability and not so much on the xylose variability. You can see that for both the models, by the way. Which of course sort of confirms that what I would like to investigate is the case. That's really what I am investigating. If you could go a bit back here to the whole process and why these results actually made sense. Both Sander and Jan were very happy when we found these results. So we have here, so what we're measuring NIR directly on the hay, and we're not measuring it on what we're doing with the enzymes. So we want to have it all the way from the raw. Now these enzymes, they have different activity, and it turns out that the conversion from hemicellulose to fructose or to xylose here, that is almost, to xylose, it's almost complete. It's very efficient. On the other hand, the conversion from the cellulose to the glucose, that's a bit so-so. And of course here we're not measuring the NIR spectra here of the xylose and the glucose directly, but we are measuring hemicellulose and cellulose on this straw. And since there is a direct link here between the amount of hemicellulose and the amount of fructose we get at I don't know why I keep saying fructose. Xylose, sorry, at the end of the day, it also makes sense that we can make a nice causal prediction model here. On the other hand, to the glucose level and the cellulose level, they're not really, it's not a one-to-one relationship. It's very dependent on how efficient these enzymes can be on the straw when it comes to converting the cellulose to glucose. So at the end of the day, this made very much sense also going back and looking at how these samples actually were prepared. Now, as the last example, I would like to bring attention to another paper that I just recently published together with Jing and Sander. This is on something called POC, which is a subpool of the soil organic matter. And a lot of soil scientists are very keen or very curious about this POC because that sort of can give an idea of how labile C or active C is related in the soil. So they want to look at how much active carbon there exists, basically. Now, if you just look at some reference analysis on the soil organic carbon here versus the POC, we can see that there's a very high correlation between the two. So obviously, if we can predict one, well, we can also predict the other, just as I have stated earlier. Even though the amount of POC is way less than the soil organic carbon, it has to be, right? Because this one is a subpool of the other. So what we thought of here, this has gone through many iterations before we came here. We wanted also to try to make it rather simple, let's say, and I think it's sort of, you can judge if it is simple or not. So what we made here was that we have the FTIR data of the soil samples, and then we have the measured POC, and we have the measured SOC. What we did was that we made a PLS model towards the SOC and another prediction model to POC. But just basic PLS models, nothing very fancy here. Of course, determining the number of components and so on for the different two models. Now, what we can then have, we will then see what we have here. We have on one axis, we will then have here the regression coefficients for the SOC, and somehow related, since there is a correlation between the two, we will have the correlation coefficients for the POC. Now, of course, I can then divide this correlation coefficients, regression coefficient, into being parts that is called partly with the BOC, which is down here, and some part that is orthogonal to the SOC. We can then, what we mean is we can then take our regression coefficients, the total regression coefficient of the POC model, and can divide it something that is parallel. Now this one here is related directly to the SOC content, and this here is then unrelated, at least to the regression model. And then of course we can then translate it here again directly into the SOC and the POC. Another nice thing of this rather simple, I would say, procedure is that we can get an idea of how much of this model, of the POC model that we have up here, up in the top here, how much of this model here is unique. Because now I can say, okay, how high is this one compared to the length, the length of this POC here. That's what I have here, and it says 11.3%, which indicates, of course, that most of the prediction model of the POC, or the regression coefficient, is related to the regression coefficient of the SOC. So they're highly dependent, but it also seems that there is some uncertainty here. Another good thing about this procedure is that you can easily apply cross-validation on this. You can do all the different styles of resampling that you would like. You can validate it in any way you want. So I even have some uncertainties here on this 11.3%. It was significant. Now what we can see here is then up on top, let's just focus on the two first rows. Then we have the PLS model on the SOC and the PLS model for the POC. That's what we have in the top, and you can see that the R squared here, well, they're fairly high for both of them. Yes, you can see that they're very different in the numbers and the RMSE values, and that's just because they're in different units. It doesn't mean anything more than that. Now, the last line, that's actually the SOC model, but I'm only looking in the direction of the POC. So here I'm only looking at what is related to the POC, and you can see that it is a bit worse than if I'm building my model on the POC directly, but this is an indirect model where in principle, I'm just predicting my SOC and then multiplying by some numbers to get my POC value. And I do get quite close. I mean, I do here have an R squared of 0.81 instead of 0.85. So meaning that most of the model actually comes from the correlation to the SOC. But at the same time, it also means that there's some part here that seems to be directly related to something else that is not soil organic carbon. And again, here you can then apply all like a jackknifing type of procedure, which is what we did. And we then try to look at, okay, so where is this unique signal? So in this figure, I think again, I need to sort of explain a bit what we're looking at. We have then the epoxy model, which is the blue line. And then I have divided that into what is related to the SOC calibration model and what is unique to this epoxy. And you can see that there seems to be a bit of signal here around 3,600 reciprocal centimeters, but the main uniqueness is around here in the fingerprint region. And for those of you that are working a lot with spectroscopy, and I heard at least some from Foss earlier, this area here can sometimes be a bit tricky to measure, and especially for soil samples. Now in this example here, the instrument that Sander has access to gives very nice signals also down here in the fingerprint region. And that's thanks to that, that's when we can also see some unique properties down here. A lot of the other instruments that have been used in soil science, they don't give very much good signal below 1200, so to speak. So it is doubtful that many of those that have claimed that they're actually looking at nice predictions models of POC, that they actually have been looking at this unique part of it that we can see very far down here in the fingerprint region. It's just to sort of indicate that there's a lot of claims out there in the literature, and some of them, yeah, they do hold, but you also need to be a bit careful with and read carefully with what people are stating. Now, as I mentioned in the beginning, I would like to also talk you to some of the orthogonalization methods, because you could just state here, if you just look at how I have looked at the problem or the challenge, well, I'm doing some orthogonalization, right? I'm having the POC signal as an orthogonal component that is not related to SOC, and one component that is related to SOC. And this is an orthogonalization thing. One component is orthogonal to the other. And this has been addressed in literature for many years. And I just want to bring your attention to a few of them. Now, I want to bring the attention to a few of them, but that does not mean that I have studied them in detail. So what I want to say now for the next couple of slides here, I want to just say that I haven't done this thoroughly. So this is a bit based on experience that I have made during the years. And others I can also stand behind, and I can also back up on my claims. So we have here on the different methods that I want to look at. I want to look at the four uppermost ones. So we have first one that is sort of using the Y that we're interested in, it directly in the orthogonalization. So we have something called orthogonal signal correction. We have direct orthogonalization. So here we have, this is a method here by Svante Boll. And again, here we have from Klaus Andersson. And lastly, here we have from Johan Trygge and Svante Boll. Yeah. And then I will also talk very briefly on method here called when you have the orthogonality constraint PLS model. And in reality, you can also use the extended multiplicative scatter correction for similar ideas, just like Harald Martin showed in the paper on EMSC. You can sort of get part of your correction can then be to some interferent that you're not interested in. I will not go into that one, but just to sort of bring your attention that that's also possible to do in an EMSC. Most people don't use that part of the EMSC, but it is there. Let's just try to go through these four methods. So first, the orthogonal signal correction. And the whole idea there is to try to find components that are orthogonal to your Y. So what you do, you then have, you make a PCA on your X, one component PCA. Then you take these scores that you have and you remove any information from Y in those scores. So you project your scores onto Y and then you remove that. From that score, you can then calculate your W, just like you do with a normal regular PLS model. And then you iterate until you have found this T-OSC that I'm writing here. that is then orthogonal to the y of interest. Then you can deflate by this, and you can continue. You can calculate another OS component, or you can stop whenever, and you can make your PLS model with this deflated x. Now, this method has not really been very much used. It is sort of the basis for the OPLS model later on. And I have, from my experience, and this is really only my experience on a few data sets that I have played with this, it doesn't really work. It doesn't give any increased interpretability, which is a claim of all these methods. And it certainly doesn't give any gain to the predictability. So prediction results are, in my mind, is quite often worse. And the really difficulties here is finding, okay, how many of these orthogonal components would you like to extract? And of course, you can apply a cross-validation across all these to sort of figure out what is related and what is not. But you then have to optimize two parameters, both the number of OS components and the number of PLS components in your model. And of course, it is, when you do the test set validation, it's highly dependent on the relationship in your Y, so the correlation that you had in your calibration set and the validation set. Now, Klaus Andersson then 2 years later came up with something called direct orthogonalization. Preprocess, that's the PP, you preprocess your X and Y, and then you project your X on the Y to get loading weights, and then you subtract that. So this is based on the direct covariance between your X and the Y. And then you get then you subtract that to get, so they get something called XO, you can also call it X orthogonal, which should then describe any other variability than what you're interested in. Now he suggested to do a PCA on this orthogonal. You find your scores and your loadings. You actually don't use the scores. That's why I haven't called them TO. You only use the PO. Then you project your original X onto this, and you find your then orthogonal scores. You deflate with these ones, and then you have an X here that he is calling, then this has been direct orthogonalized. And then you can predict your Y from this one again. Now, if you go back to the interpretability, it may be that this gives an increased interpretability. I'm not completely sure, but I don't think you get an increased predictability at least. So you don't gain anything with regards to that. Then we have the OPLS, and I think many of you have heard about it, or most of you have heard about it. A few of you probably know the algorithm, which is not super important, but what you do a one component need pulse, so PLS, and then you orthogonalize your loading, so the X loadings with regards to the W, so the loading weights, and you get a set of what they call orthogonal loading weights. Then you project your X on this, and you find your orthogonal, and you project your X on the orthogonal scores, and you find your orthogonal loadings, and then you can deflate. And then you can deflate this as many times. You can keep on doing this for as many orthogonal components as you like. So you can see this method is very much related to the OSC that also Svante suggested some years earlier. And then what you can do at the end of the day is that you can predict your Y on this deflated X data. Now the claim was back when this came out. The first claim was later withdrawn by Johan nicely at an SSC conference. Now I don't remember exactly which conference, but some years later, because it was stated that this OPLS could give a better predictability. It doesn't. It gives exactly the same prediction ability as a regular PLS model. The only thing that it does is that it's going to divide your data into your orthogonal scores and those that are related to the Y, meaning that you only have one predictive Y component and the rest of them will then be on orthogonal. And then there's a question about, does it increase the interpretability? Because now we can look at how does this regression coefficient of the one component that actually is predictive, how is that related to the Y? Well, if you look into the math here, what it actually can show here, again from some data on Bali, is that if you just look at the covariance matrix between your x and your y, it's exactly identical to the OP-less regression coefficients. That's the orange line here. They are on top of each other. There's no difference. This is from a different work I've been doing. So don't, the red one is just the correlation between x and y. That's the only difference. So here we have also taken into account variability. But just to state that it doesn't even increase the interpretability, because you could just have looked at the covariance matrix to start with, and you would have gotten the same information as you can from the last one, the predictive component. Now the last method, and this is one that I haven't looked into at all, so I don't have any practical aspects or comments about this. But the idea is quite nice. So you have here, you have your x and your y, but you then also have a spectra of an interferent that you're not interested in. You don't want your model to be influenced by it. And what you can then do, you make a projection matrix, which is this one here. What it basically means is that it means that you will project your data onto the spectra that you're not interested in. You calculate the scores and the loadings, and you can subtract that part of the data from your model. Now, what they do is actually they've implemented it within the Nepal's algorithm, meaning that every component that it spits out will then not be affected, will always be orthogonal to this interference spectrum. And I must say, at least the interpretation of this, the final model, in my mind, sounds a bit complex, but I'm sure it can be done. Predictability, I don't know, it seems like it's at least what they show, at least in the article, is that it's more robust to variability. But of course, in any article, we propose a new method, you want it to shine. So sort of course, take that with a gram of salt, but it looks interesting, and I kind of like the idea. So I think it would be nice to dig more into. So summary, all the way back to the data. So we have this guy that had 24 samples and had 32 reference analysis, and he made 32 PLS models, and they were all working great. Now, is there a problem? For sure, all these 32 models that he did create, they cannot be independent, because there's only 24 samples, meaning that the rank of the system is 24, unless you start doing pre-processing, and then you start to tick down the degrees of freedom in your data set. Now, is there a problem? Well, it certainly is a problem, and also shown by the first fatty acid profile data. If you then start changing the covariance of the Y in between the samples in the future, then your model will break out. And this is not very new. I mean, that's what we really claim when we're doing chemometrics. When we get outliers, we get samples that are outside of the covariance that we're looking for, we can spot them easily. We call them outliers. Well, now we will have it in Y instead of in X, but it's the same. So if we get some break of the covariance that we had in the calibration set to the new samples, we will then have a problem, and we can't give a nice prediction. However, on the other side, if we know that in the future, we will keep having the very same covariance matrix all year after year, it's not a big issue, because we can still get reasonable predictions. We should just be aware that the model is actually not directly predicting what we are giving out as an output. It's indirectly related. Right? It's based on some of the major components that we have in our samples. So with that, I think I would just like to finalize and just show the faces of the four of us that are the chemometric group here at the University of Copenhagen, that being Frans, Rasmus, me, and Morten.